All right, I'm going to take this time to look at Rolle's theorem and what it looks like in practice. This is a function 1/2 of x minus root of x. We're being asked to first verify that Rolle's theorem applies on this interval from 0 to 4, the closed interval from 0 to 4. And then, if so, find the value of c that's guaranteed by the theorem. What Rolle's theorem says is that if you have a function that on a given interval has the same y value at the beginning of the interval as it does at the end of the interval, then something possibly could happen. So let's first verify that that's true. Let's see what happens at f of 0, which of course is 1/2 of 0 minus the square root of 0, which is 0. So now we need f of 4 to be the same. It's got to also turn out to be 0. So 1/2 of 4 minus the square root of 4, and I think you can see that's going to be 2 minus 2, which is also 0. So here's our first condition that has to be true, is that the endpoints have to have the same y value. So we could go ahead and take our little coordinate plane and put a point there and a point there at 0, 0, and 0, 4. Now, the rest of the theorem says that as long as you have that true, that the endpoints are true, and that the function is continuous on this closed interval from 0 to 4, in other words, there's no breaks in the graph from here to here, and I think you would understand that's certainly going to be the case. Half of x is continuous, root of x is continuous as long as you're positive or 0, and of course we are only talking about positive numbers and 0 here. So both of those are continuous, so the difference of those two functions is going to be continuous. So we're cool on that part, but the last condition is that it has to be differentiable on the open interval between 0 and 4. In other words, we don't have to worry about the slope at the two endpoints, but we have to make sure that nowhere between 0 and 4 will this thing have an undefined slope, because that's what would make it non-differentiable. So let's look at the derivative of 1/2 of x minus root of x. So f of x is, we're going to just rewrite it as 1/2 of x minus x to the 1/2. So f prime is 1/2 minus 1/2 x to the negative 1/2, which of course means 1/2 minus 1 over 2 root of x. So if you're thinking about the derivative and making sure that it's defined everywhere, you'd say, well, wait a minute, we have a problem here because we're dividing by a variable. If that thing's 0, this thing's not going to have a slope. However, the only time it's going to be 0 is at x equals 0, and since that is at the end point, we're not worried about that for the differentiability part. We're only worried about are there any places between 0 and 4 where the graph is not differentiable. The only place that this is not differentiable is at 0, so we should be good to go at all the other places along the way. So what it's saying is that this curve is continuous from here to here. So it either comes up and comes down, or it goes down and comes up, and somewhere between these two, because our average rate of change between these 2 points is 0, somewhere there's got to be a 0 slope. There's no sharp corners, there's no breaks in the graph, because it's continuous and differentiable. So we just have to find that spot, and that spot, that x value where that's going to happen, is the spot guaranteed by the theorem. So what we're going to do is take this derivative and set it equal to the average rate of change that it's experienced between these two endpoints, which of course is 0. And we'll see if we can solve this. So let's set this guy equal to 0, and then we're going to add the 1 over 2 root of x over to the other side. I think you can see that x equals 1 is going to work, but let's cross multiply just so you can see that 2 root of x times 1 is equal to 2 times 1. Divide both sides by 2, and you get root of x equals 1. Square both sides, and you get x equals 1. So what's happening is this curve gets from here to here, and so it experiences a net average rate of change of 0. However, at x equals 1, the slope is going to be 0 as well. And for what it's worth, this curve kind of looks like a Nike swoosh sort of thing. It comes down and then goes out like that. So right here at x equals 1, that's where the 0 slope is. So the value of c, guaranteed by the theorem, is x equals 1.